Well, yes, welcome everyone to GeoHug. So before we kick off today's session, I just want to take this time to acknowledge the traditional lands which we're all coming from today. I live on the beautiful lands of the Gadigal of the people of the Aurora Nation, and I'd like to pay my respects to the elders past, present, and future. And so I am so excited to have Marcus Bueno joining us today. So Marcus is the founder and CEO of Geopyörä, a startup focused on developing innovative and cost-effective rock breakage testing solutions for the mining industry. So with his 17 years of work and research experience in mining and mineral process engineering, he has in-depth knowledge of the design and optimization of comminution circuits as well as geometallurgy. So it is going to be amazing to hear from him today about the why and how to do breakage tests of geochemical samples. So I hope you all enjoy it. Please use the chat and we'll open up the floor for some discussions at the end. And yes, thank you so much for joining. It's wonderful having you, Marcus.
Well, thank you, Jessica. Thanks for inviting me. Thank you everyone for joining. I join you and acknowledge the original owners of the land, people that I used to love to chat to and interact when I was living in Australia. So first I will start with the name of the company and the technology. We baptized it Geopyörä. It has something of me in it, and something of Finland too. Pyörä means bicycle, and you know why I will gave this name. Is because the machine used two wheels, it resembles a bicycle, and my biggest passion and hobby outside work is cycling, so made a lot of sense to baptize it Geopyörä. And today I'm going to talk on why and how we should use drill core samples for breakage testing, the geomet assay samples. And a little bit about me. So I spent most of my career in Australia. First, I went there to do my PhD at the JKMRC in the University of Queensland, and then later I worked for Ausenco as an engineer, doing all sorts of technical studies and also full engineering projects in green and brown field. And more recently, I spent some years as a researcher and lecturer here in Finland, which is where I developed the Geopyörä technology. So about this conversation should be about breakage tests and comminution tests. There are many types of comminution tests out there. But most tests, they use a lot of mass. So you have grindability tests, which can be the most famous is the bone test, where you need some sample to grind in a little mill in the lab. You have a single particle breakage test, such as the famous JK dropweight test or the SMC test from Steve Morel. You have even a smaller test introduced by Tony Kojovic, who was my supervisor, called HEAT. And there are many others which are equipment specific, but anyway, the idea of using this test is to characterize, measure something about the relationship that you have between energy and fragmentation in comminution. And then all these tests, most of them are not very appropriate for geomet. We still didn't have a perfect test for geometallurgical testing, and that's what we strived for when developing Geopyörä, because the whole idea is that we would be able to model in a block model with high resolution, spatial distribution resolution, rock hardness properties, something that's not really done today. You model really well grades, but you don't do that with hardness properties. And then I would like to talk a little bit about what would be an ore type, variability in terms of comminution. Is a lot led by the texture, which is basically how the different minerals associate with each other in a rock structure. And then we would need to understand how these different textures they would behave in terms of comminution. So that's why we need to test really small samples, because typically in comminution you end up compositing a lot of material in large samples that sometimes weigh up to 50 kilograms, and then you'll be mixing a lot of different textures, different mineralogies, and then you end up having averaged results that not always will be representative of the variability of true variability of the hardness of rock in mines. And then there are kind of typically two types of hardness when you talk about hardness or competency of rocks. And then here I have a chart of some database from my time at Ozenko, where in a test work where we did a lot of SMC testing, measuring the drop weight index parameter and the grindability test of the bone test to measure the bone work index. And there are rocks that they can be very hard to grind, meaning a high bone work index, but they can be quite friable. They can in a macro scale, like in a drop weight test, breaking coarse particles, they can fragmentate quite easily. They have a low drop weight index, and vice versa. So we need to measure these two properties and be able to see how they vary from mineralogy to mineralogy and spatially as well in our body. And that's the whole reason why we developed the Geopyörä breakage test, to understand this variability so that we can assure productivity through the life of mine. And I used to have this in the opening lecture of my classes in the university for feasibility studies, which is from Adam Smith. For those who don't know, is the author of Wealth of Nations, which is considered being the beginning of the modern concept of capitalism. And then he has this statement about mining, where he's kind of pushing people away from mining, not to engage, advising people not to engage in mining because of the risk and uncertainty involved in this activity. And so that's the whole context. Here in a summarized way, usually mining projects, we test tens of thousands of geochemical assay tests, and we've been looking very closely to this figure. So we being compiling a database of feasibility studies, of all feasibility studies published under the NI 4301 and JORC code, both in the ASX and the Toronto Exchange as well. And basically, we're looking at the ratio of how many samples were tested in the development of the feasibility study to understand the geological grade model, the resource model, and the tens of thousands of geochemical assays for one single comminution test, which is kind of a huge discrepancy. And basically comminution is being neglected, mainly by the fact what I was mentioning before, that a technology that were existed before Geopyörä, they were focused on measuring a few representative, a large bulk composite, geochemical samples. And then you have a no understanding on that variability, and then you have uncertainty on on the size of your mill, on the throughput through the life of mine, which bring a lot of risk for the finances of the mine, in the whole finance model, which depends on revenue rates that are closely linked, directly proportional to the rate at which you can grind rock. So I believe that you test way more, to be able to understand this this variability and maximize project value. But for that, you would need a low-cost breakage test. There you can see the Geopyörä, which is in Brisbane, this one, and to test small discrete samples. We are here proposing to test the same interval sessions, a short interval sessions of 1.5 meter that are used for geochemical assaying, do very good accurate measurements of Geopyörä, and then generate a large volume of data, which would be ideal for geometallurgical application. And now even trying to push it forward and develop an online testing device, a sensor, and I will mention more about that in the end of the presentation. But here is the difference in approaches. So normally as I said, you test a few large composite samples, which would be expensive. It takes a long time for you to get results back, and then you end up get one average a result, and then you have some kind of empirical parameters that comes out of these tests. And that's what is used today, for you to predict energy consumption, for you to forecast production and so on. And we are proposing to use these small samples and do it fast. We have the results like very quickly, like the turnover, and then you have data like to either design your project accurately, like precisely, and in terms of forecasting of a new project, or in terms of like optimization of an existing project. But how does the Geopyörä works? Like, what's the principles behind like the testing with Geopyörä? As I said, it uses like two counter-rotating wheels to crush rocks one at a time, and then we record like the energy that was consumed during breakage by observing the loss of momentum of the wheels. And then we also measure the force applied during breakage by observing the bending of one of the structure during the breakage. Like we have strain gauges, and then we capture like the force that was applied. With those two measurements alone, we are able like to derive like most like a comminution parameters from standard comminution tests, such as the drop weight test and the bond work index grindability test. So basically you end up getting like with one test, like one test that is a quick and fast test that you can do. You can get like many parameters out of the test. You can get impact breakage parameters, you can get grindability parameters, as well as mechanical strength parameters. So basically is way more value for the investment, and you would get all these results on the very same sample, which you would do a geochemical assay. So, because like, what's the procedure? We can get like this 1 meter, half meter of like of half or quarter core, and then we crush this core like in a controlled manner using a jaw crusher to obtain small particles, and then we use these small particles in the test work. And so, and then once we finish our test, the sample can go back to the queue on the geochemical assaying procedure, because as I said, like you have tens of thousands of samples to assay. So you have a queue like in the assaying lab, and like what you're proposing is to be doing the test work in parallel, and that wouldn't delay in any manner like the workflow at the assaying lab. We would be able like to conduct like the breakage test, have the results, and that sample after the breakage test is reconciled, like the broken particles that we haven't used in the test, everything goes into the same bag and is pushed forward to the assaying lab to complete the procedure. And then all the data, like we created also like a data processing and analyzing platform, which is hosted on the web in Microsoft Azure. So the laboratories, like for example, Core Resources in Brisbane, they can upload like the raw data from the test work in our system, like in the so-called like a geodata, and then they are able like to immediately get the results like of the test, the parameters that are generated from the test, and then be able to report that to the client. And this data can be visualized, can be analyzed like in this online platform. So let's talk a little bit more about validation, because we are proposing something new here. And then I know that the industry has some like a reluctance in moving away from the traditional testing methods. So we've been doing in the last 2 years a lot of validation and comparative work against like traditional methods. But before I go into comparative, like I want to talk about on what we are different, like how different we are. Like so normally like a test, like you would do a test in the lab, like we spend like a day or two testing a sample, like in a bond work index, like experiment, or in a drop weight test in the lab. And then you would finish the test and you would have one averaged calculated parameter. And then in our methodology, like as I said, we are measuring force and energy. So we have actual measurements, which differ us like completely from other tests in the available in the industry. So, and when we are measuring these numbers, we're measuring for every single particle within a sample. So we generate these distributions of like force and energy for a given sample, which is almost like a probability of breakage. well, it is a probability of breakage within that population of samples that we've tested. And then we can, with that, like differentiate samples, even if we have just a few samples. We don't need to do repeats. Like so, if you do like if you test sample A and sample B, you can already like either visually by plotting these distributions or statistically by doing statistical tests, confirm if they are different or not. But if you do a bone test or a drop weight test, like which are the two most used tests out there, you practically don't get like you are not able to differentiate. Let's say you do a bone test and you get like a bone work index of 15 on sample A, and then you do another bone test on sample B, and then you get like 16 and a half. And then you ask yourself, are these samples really different from one another? And you cannot answer that question. You need to do like a few repeated tests like on each sample to be able like to do a basic statistic, at least as a minimum of 3 on each sample. While here, like with one measurement on each sample, we can do like ANOVA if we have a few samples. If we have 2, you can do a student test. Or if you have several samples, you can do multivariate data analytics and classify them, group them into samples that behave differently from each other. With statistical meaning and significance, we can do that. But now the comparisons, like so the big first comparison that we did was we are measuring energy, and there is not real way for us to do it more directly confirm if the energy we're measuring is really accurate. We can see that it's really precise, it's really reproducible, like to the point of like a 0.1 joule. But the thing is that we need to, by some means, like try to have an indication that like the energy we're measuring was accurate. So like if we measure 1 joule, like is this like 1 joule that was consumed in breakage real? So to do so, like we did that in an indirect way. Like what does that mean? Like we got like a number of samples from different deposits, and then we tested them like in the Geopyörä, which differently from other tests, we are measuring the energy. It's not an input. And then we send the same samples, duplicate samples, to a drop weight tester, where the energy is an input, like it's a nominal amount of energy that's given to the rocks. So basically, the mass and height of a weight dropping onto a rock particle is adjusted to give a certain amount of nominal energy to that particle. And then we adjusted the mass and the height of that like drop weight to provide the same amount of energy that was used, that was measured like in the Geopyörä. And then we expect that like for the same energy, you get the same fragmentation. Fragmentation here represented by this T10 parameter. What's the T10? It's the percent passing 1/10 of the original size. So basically the amount of fines that were generated out of that breakage event. And then we obtained the same T10s. So which means that like our energy measurement was accurate. The other like exercise we had to do was to confirm the ability of us to regress the parameters A and B, which is the parameters that define hardness, competency in the drop weight test method, which is linked to this equation, which was introduced like back in the 80s by Narayan and White in like a JKMRC. It's the so-called breakage equation. Basically, it's an equation that relates the T10, the fragmentation, with the energy applied. The drop weight test uses like 15 points, like data points. Like they use like 5 different particle sizes. They apply 3 different energy levels per size. So they have 15 data points to fit this curve. And then we are feeding this curve with only 2 data points. We test like one set of particles at a higher energy level, and one set of particles at a lower energy level. And although like we are only measuring like 2 sets of points to fit this curve, we were able to fit like reasonably well like for many different materials. Here we have like 2 fits like as an example, but the complete database is capturing this figure, where so to date like we tested more than 200 samples for validation. which were test work that was required by many of our customers in the beginning. They were wanting to know if you'll be able to generate the A times B parameter accurately. And then they did test with samples that they had already previously tested with the drop weight test or the SMC test. And then we tested on the Geopyörä, and then we were comparing basically what was the A times B derived by our method in comparison of the A times B that they had from the traditional drop weight test method. And then we get most of the mean relative error of 11% and most of the results within plus or minus 15%, with a few outliers here and there. And then there is the SMC test drop weight index parameter, which is simply an inverse of the A times B. And then similarly, we got most of the data within plus or minus 15% and a mean relative error of 13%. Keeping in mind that round robin exercises done by JK Tech on estimating the reproducibility of the method is in the order of 7%. So even if you are repeating the SMC test, you would have a plus or minus of 7%, which is not far away from our mean relative error in this validation database. And then in terms of bond work index, and here is I used to call this the cherry on top of the cake, because we are doing an impact breakage test, and the bond is a grindability test. So we would you're not performing the same type of a breakage mode. We're not grinding the material, we are just crushing it. And then we were able to predict it in the following way. We looked at the size specific energy, which is a parameter that Grant Ballantyne and Professor Malcolm Powell introduced a few years back, which is basically kilowatt hours per ton of a certain size. In this case, we're getting the 150 micron size. So we look how much material below 150 microns is generated during the test, and we know the energy consumed in kilowatt hours per ton, and then we calculate this a kilowatt hours per ton of sub 150 material. And then that has a good correlation with the bond work index itself, which you see in the bottom right hand corner of the screen. If we derive a simple quadratic equation, to second order polynomial, to that data. And that's what we've been using to estimate the bond work index with a mean relative error of 7%, which is pretty close, again, with this reproducibility of the bond work index test itself. The most recent data, published by Tim Viscara, works for JK Tech, he published that in 19. In round robin tests, it's about 6%. So we are almost as precise as the bond work test itself in predicting the bond work test, the bond work index. And then there is a parameter called SGI or SPI, which is some sort of grindability test for SAG mills. We still don't have much validation here. This work was done for HUD Bay, could be using this parameter. It's mostly used in America. And then it correlates with the specific energy, and we managed to develop a simple model for them, so that they can have the parameter they use by doing the Geopyörä and looking at the energy consumed. Here's just a summary of these validation results that I've just mentioned. And I'll go through some case studies, some applications of the Geopyörä that we had in the industry so far. The first big one that we had was a geomet program for Agno Eagle Kitla, where they sent us about 1,000 samples. They collected drill cores specifically for this purpose. They did a drilling campaign, and they cut the drill cores in half. And then on our half, we did the breakage test. In their half, they did a XRF, and they did a few XRDs, mineralogy, quantitative mineralogy on a few samples. And then with this volume of data, 1,000 data, one-to-one, a geochemical and breakage information, we managed to develop a very good, robust geometallurgical model where they can predict the hardness of the rock, using the geochemical information that they already have in a very high resolution in their block model. This work we're going to publish later this year in Canada, like during the SAG conference. And then there was like the Sakati project for Anglo America here in our backyard in Lapland. It's a multi-metalliferous deposit that's being developed by Anglo American. There you can see some drill core scanning pictures like from their drill cores. Like it's a highly variable deposit. And then they sent us like 300 samples, like a 1 meter intervals like of samples. And then we tested those, and then I just would like to emphasize that 300, although 300 samples in terms of particles tested, like were like more than 8,000 particles, like that we actually did measurements. So like we had a very large volume of data to be able to domain like this material like into 5 classes of according to hardness. And then there you can see the distribution of the energy kilojoules per ton for each particle measure, like in these different classes. They really set apart. And now, like what like Anglo is doing, they are looking into the mineralogy of the product of this breakage test to develop like this correlation on how mineralogy, how the geochemistry is driving the comminution behavior. What is different in these very hard like particles that you don't see, for example, in the very soft, and vice versa. So that's the principles that like they are trying to apply in a feasibility study, and that like something that's not like typically done in the industry. And then Copperstone, like it's a copper project like in our neighbor country here in Sweden, in the Lapland too, like near Kiruna, where they have the famous like a magnetite like mine. And then they are developing like this copper project. And then they already tested 120 samples with us, and they are going to send another 2 batches of 120 samples, like totaling 360. But then like they did like some benchmarking tests, like against SMC and bond, which were close, like they related, like and that gave them confidence. And then like they're now using like our data like to develop a mill throughput model, and then develop like the flow sheet. And then this data is being used by their engineering company doing the project, which coincidentally it's Ozenko that's working on the project now. And then Cobre Panama, like they heard about our technology, and then they approached us. Like we tested initially 126 samples in an exercise of like comparative work against SMC and bond. The work was done in a lab where we had our machine like in Germany. And then they gain confidence like to take the device to site, like and then you can see like in the picture there like one of their technicians using the machine like in Cobre Panama. And there is a picture of myself like on a drilling bench, on a drill and blast, like a bench that was being drilled like to load the holes for blasting. And the procedure there is to do in Cobre Panama is to do recurrent testing, not using the drill cores. The drill cores they are using to develop a satellite project. Like they are doing like they have 2 big deposits in Panama. One is Botilla and the other is Colina. And then like La Colina, they are getting drill cores to help them develop like the throughput model like for this new project, the new deposit they're developing. But like for the current operation, the current pit, like they are taking daily like a drill and blast chips. So we take like a screen to the pile, the muck pile that like sits around the drilling hole. And then we discard the fines, and then we just bring like the chips, like the coarse rocks, like into the lab, which are tested, and they have results like immediately like to already inform the drill and blast team, so that they can do like already optimize like even the drill and blast like by loading like harder zones of the bench with higher loads of explosive and the softer like more friable areas like with less loading of explosives. And they can also track this information of the ore hardness all the way through the mill feed. And then we are developing predictive like throughput models for them. Right. So let's talk a little bit about like our business model and how we are bringing this technology into the industry. Um, our business model is very simple. Like we're offering like the testing service to mining companies, and here is a snapshot of all clients we have had so far. So like all these companies have already like used like the Geopyörä test in a way or another. And then we mostly do that like through licensed laboratories. And in Australia, like our licensed lab, like Score Resources, Rob Coleman, like he's here in the seminar, like he can be reached out, like if you have like an interest in doing the test work in Australia. So simply we license the technology to these laboratories for them to do the test work for mining companies. We license the technology for a fee, and we charge a fee for the analytics that we do to report back on the standard comminution parameters. But we also can license technology directly to mining companies, as we did like for First Quantum Copper Panama, where they are doing the tests in-house rather than sending samples to a lab. We also have like a global pricing strategy, like so our prices like are the same in Australia or in United Kingdom or in Africa or in Canada. So we keep like our prices standard globally, and then we also introduce like a economy of scale in our pricing strategy. So we want to encourage the mining companies to reach higher volumes. And then coming back to the whole purpose of this talk, like which is to say why we need to test like the drill core samples. So simply because like they are early on in the early stages, you are doing assaying, like so you already have that sample, which is today it's dumbly crushed. They only crush it like to subsample it and then pulverize and do a geochemical assay, either through ICP or XRF. And we want like to propose to use the same samples to be able like to change this paradigm, like where you test like tens of thousands of geochemical assaying samples and a handful of comminution samples, and you have a huge uncertainty on the hardness of the rock. And then if we get like let's say 1% of the volume that's typically tested in a project for geochemical assaying, we would be in the order of 1,000 samples. And that's the number that we are trying to reach. Like we're trying to get like to these volumes, and then to encourage customers to make this at an affordable rate. We introduced like this pricing model, like which reduces our margins as the volume goes up, but like it enables like and make it affordable for the mining owner, the project owner to reach these higher volumes and test more. Here's just a comparative of competition. Like the typically people do SMC and bond, and that's why people don't do hundreds or thousands of like SMCs and bond tests. Number one, because they need like a separate sample. They don't use the geochemical assaying samples for this purpose because they need to composite. They need a large amount of mass. They need like tens of kilos. And another point is the price. Like it costs like quite a lot, like more than 3,000 euros. Like we're talking about nearly $5,000 to do a set of SMC and bond on a sample. While with us, like if you reach like the thousands, like can get like as low as lower than 100 euros like per sample. So the value proposition of doing that, like the why, like do like the test on the geochemical assays and get higher volumes of samples, is simply like to get way more data for the same budget that you would normally use on a test work, and that will allow you to do a more robust data analytic and modeling of like the resource, so that you can reduce the risk on investment when you are investing like hundreds of millions or sometimes a couple of $1 billion in a new mining project. And then that you can operate the whole operation, like which normally you have like it's quite standard. Like there is even like our friend like from giving seminars about the money mining, like the people from Whittle, Jared Whittle, talking about like optimizing like mining scheduling, like to go to seek like the higher grade ore first. But grade is not like where the value lies. Like grade is part of it, but like the big part of it like is hardness, because that dictates operating costs and the production rates, like the revenue rates. And with that, you could like by seeking like by searching like the high grade, like easy to grind material, you can optimize the NPV of the entire project. For laboratories, like adopting our technology, like for like core resources, for instance, there is a lot of value, like in terms of cross-selling, like they can offer the test like on samples that they would do other test work, they can do on the same sample. And then we have our commercial effort of like bringing customers to the laboratory. And in the beginning, like we don't want to create competition in a certain region, so we give like to the labs like exclusivity like in the region, like as we gave like for core resources in Australia. And we keep our prices like a table, like so that like a customer in Australia will not feel tempted in sending samples to, let's say, South America, because it'll be cheaper to do tests there rather than to do with Rob Coleman like at core resources. And then we try to stay ahead of competition by always pushing further the technology, and then like firstly like to hold patents on what we've developed. We have patent application in multiple countries, and in Australia the patent has already been granted. And we have this always investing like in QA QC, like in methods like on how to make sure that the machines are running in order. To make sure that they are running like measuring energy and force precisely and accurately. And we are also pushing for the development of the device itself. Like, so we had a first prototype, which like we did a little bit of like a product engineering on it to come up with the first version for commercial use, which is the one that's available in Australia. And we are about to release like what are so calling like the 2.0 version, which will have like a fully integrated like a feeder, so that the operator simply has just to put the particles in that feeder, press play, and the machine does the job itself. And then like that will reduce operating costs and make the test even quicker to do. And then I want to talk about another technological development we are seeking, which is partnering with core scanning technologies. And the one that we're talking the most, and we are very well aligned with Minalize, like is the company of a good friend of mine, Anneli, which might be known for some of you. And they do core scanning with in combination with like XRF scanning of the drill cores. And why we want to do that? Like because they can do that almost inexpensively through kilometers of core, and then that would allow us like to even testing a much smaller volume of samples in comminution than we would test in geochemical assaying. Like so, in average, like a project test like tens of thousands, like hundreds of kilometers of core assayed in every meter or every 1.5 meter interval. Like they will not do that in terms of comminution, and don't even want them to do that because it's not really needed. Like, so the idea is that like we would like of course scan all the core, and then we would select like that would help us actually like already before testing already to understand like to domain like the core like into different textures, different mineralogies, and then we'd be able like to select a large enough number of samples from these domains from that were identified by core scanning, to have like a really good like understanding of the hardness by doing Geopyörä tests on those samples. And then later we can develop like infer the data for other sections of core that have been scanned. So like because their scanning method, like you can get like the rock quality data, the structure logging, SG, geochemistry, the images, and all this data can be correlated with the breakage data. And then with these models, like we can predict like the comminution for further sections of core. Now, like Minalize and ourselves, we are in conversations of like with mining companies to try out like this approach in a project, to do a project together. And another technological development I kind of briefly mentioned in the beginning of the seminar is the online testing. So some customers want to bring our technology to the plant, to use it as a sensor, to measure like samples every 10 minutes, like in real time, and generate data for process optimization, and basically creating like a online like a geometallurgical lab, because we can do mineralogy on the product of like the breakage test too, and then we push this knowledge that we generate in the processing plant upstream like to the geological model, and then we also like have data to optimize the process downstream. We already raised like some funding to develop like a proof of concept prototype, which we are working right now. And then we have interest like from a couple of like big mining houses to pilot the technology at their operation. And then we have a commitment also like with the environment. Although one of the points of like develop technology was to make more energy efficient use, like a more efficient use of energy, like in the processing plants. But like in addition to that, like we decided like to donate like a part of our revenues, like to plant one tree for every sample tested with us. So we already like donated one plant like for every sample we test like in 2022, and we will be doing so like for 2023 as well. This is our team, like so I'm the CEO running the business and trying to develop the business further. Professor Malcolm Powell, who is based in Brisbane in Australia, he keeps driving us and giving direction like for our technological developments. And I have my colleague like in Brazil, Ronan, who is acting as CFO and COO, like looking into the more business administration side of the business. And we have like two trainee engineers who help us a lot and are learning with us like to be the next generation of like people pushing the Geopyörä ahead. And I'm open to questions, and I'll actually leave this video running through like while I'll open up for questions and comments.
Thank you so much.